Okay, Bismillah Rahman Rahim. Now, today is lecture number 11 of the course Hydraulics, and in today's lecture, we are going to start the next chapter of your course, that is similitude and dimension analysis. So, before we discuss the learning objectives of this chapter and what we are going to study in this chapter, first we solve a problem on the hydraulics jump. So in the last class we solved one problem. Now we solve another problem to apply the concepts that we learn in rapidly varied flow. So in this case, this is problem 10.73. So we have a wide and shallow rectangular channel with bed slope S naught is given this much, and the roughness n is equal to 0.022 carries a steady flow of 65 CFS per foot of width. If a sluice gate, which is shown below, that is adjusted to produce a minimum depth of 1.6 feet in the channel, determine whether a hydraulic jump will form downstream, and if so, find using one reach the distance from the gate to the jump. So now what we see here is that we have a rectangular channel, as it is mentioned here. We have a rectangular channel, and in this case a gate is operated, a sluice gate, which is used to control the flow. So you can see here that produces a depth of 1.6 feet. Now the question is that will hydraulic jump form downstream of the gate or not? And if the hydraulic jump forms, then what is the distance of the hydraulic jump from the gate? Means we have to locate the hydraulic jump. Clear? So now let us start solving this problem. We apply the basic concepts that we learned in the previous class. So first what we have to do is that we have to determine that whether the hydraulic jump will form downstream of the gate or not. Now discharge per unit width is given. This 65, it is small q. So we have this small q, this is equal to 65 CFS, that is cubic foot per second per foot. So this is unit discharge. Clear? Now what we have to do is that it is mentioned in the problem that we have wide and shallow rectangular channel. So it means that the hydraulic radius that will be taken as equal to the depth of flow. This is equal to y. Clear? Depth of flow. Now in this case, when we consider the hydraulic radius as equal to the depth of flow, so the trial and error solution is avoided, because the hydraulic radius, it is area, flow area divided by the wetted perimeter. So then in that case, this depth of flow, it is present in the numerator and in the denominator. So when we consider this assumption wide and shallow, then the hydraulic radius is equal to y, and we can get a direct solution. Clear? So you have already studied about this. Now what we have to do is that the depth is given, which is 1.6 feet. Now we have to compare this with the normal depth and the critical depth. So then from there we can get the idea that will the hydraulic jump form or not. So first we have to calculate this normal depth. For that we have to apply the Manning's formula. Now the Manning's formula in terms of discharge taking care of the system of units, so this is equal to 1.486 divided by n, the Manning's roughness coefficient n, into area, because we have rectangular channel, so it would be the width of the channel into the y naught, where y naught is the normal depth. So this is the area. But because we do not have the total discharge, so that's why this area we have to divide it by the width of the channel. So it becomes a unit discharge. And then hydraulic radius, but hydraulic radius is equal to the depth of the flow, because we have wide and shallow channel. So that's why this will be equal to y naught 2 by 3 into S naught 1 by 2. Now in this case, everything is known, everything is given except this y naught, and this width of the channel, this cancel out because we have unit discharge per unit width. So from here you will calculate y naught. Now this y naught, this comes out to be 10.22 feet. This is now the normal depth. If we do not have the gate and the water flows in the channel for the given conditions, so it will flow with this depth. Next we can calculate the critical depth. So the critical depth, because we have rectangular channel, for that the critical depth, that is equal to yc, and yc will be equal to q square. This will be equal to q square divided by g into power 1 by 3. Now take care of the system of units. This is important. This is where we make mistake. Now you put the values. So this comes out to be 5.08. This is equal to 5.08 feet. Now you see that y naught is greater than yc. As you can see here that y naught, this is greater than yc. So what it means? It means that we have mild slope. We have mild slope. Let me write down it here. You can see that y naught, it is greater than yc. When this is the case, so it means that we have mild channel or mild slope. Now alternatively you can also prove this. For example, how to prove it alternatively? You can calculate SC, the critical slope. We already studied about this. The formula for the critical slope, that is equal to n divided by 1.486 this is whole square into g divided by yc 1 by 3. This is the value for wide and shallow rectangular channel. This is the value for wide and shallow rectangular channel. So when you put the values here, so we will get S naught, that is equal to 0.00411. So now this SC you can compare with S naught. What is S naught here? you see that S naught, it is given by this value here. So now you can see that this S naught, it is less than SC. So this is alternatively you can prove that bed slope is mild. Clear? So this is what it means is that we have mild slope. This is mild slope. So now that we have mild slope, this is what we have determined so far. So now for mild slope, we have M profiles that will form. Now the next criteria that we need to determine is that we have M1 profile, we can have M2 profile, and we can have M3 profile. So now that we have M profiles, that will occur on a mild slope. So now which one is possible? So you have to compare the depths, because this subscript 1, 2 and 3, they represents the type. M1 means that we have mild slope or channel, and the depth is above the two. Which two? The critical depth and the normal depth. And when it is between the two, we say type 2 profile. And if the depth in the channel is below the two, the critical depth and the normal depth, we see that it is M3 profile. So now what we see is that we are given Y, and Y is how much because of this operation of the gate. Clear? What is the depth that is produced? That is 1.6 feet. So this is equal to 1.6 feet. Now this depth, it is less than YC. We have calculated already YC, and what is the value of YC? It is 5.08. So this is equal to 5.08 feet, and it is less than Y naught. It is less than Y naught. Y naught is how much? 10.22. It is 10.22 feet. So now because Y is less than both, so it means that it is type 3 profile. It is not M2 profile, because for that this depth should be between the two. And it cannot be M1 profile because the depth should be above the two. So that's why we expect that an M3 profile will form, and actually it will form. So now if you remember, when we studied about the M3 profile, when it is created, for example, for this hydraulic gate, so we have this depth of water here, and now after this gate, this depth is becomes the supercritical depth because we are forcing it. So this is a mild slope. Now mild slope cannot sustain supercritical depth. Supercritical depth can occur on subcritical slope. We have mild slope, and supercritical depth will occur on steep slope. So because this mild slope, it cannot maintain this supercritical depth because it is less than YC and Y naught. So then in that case, what will happen? It will try to increase. It will try to become this normal depth, which is 10.22 after the gate. So what will happen is that this will be a rising profile. This will be a rising profile. And because this depth, it will become 10.22, which is the normal depth in the channel for the given conditions if we do not have this gate. So it passes through the critical depth. You can see here, it will pass through the critical depth 5.08. So as a result of that, what will happen? That hydraulic jump will form. a hydraulic jump will form, and after the jump, then the water can flow with the normal depth in this case. Clear? So this is here the depth. Why not? So now this is actually what this is actually an M3 profile, because we studied in the gradually varied flow that M3 profile is a rising profile. Dy by dx is a rising profile. So now what we have determined is that hydraulic jump will form. Clear? Downstream of the gate. Now what is the conclusion? Because here it is asked that determine whether a hydraulic jump will form downstream. So downstream of the sluice gate is an M3 profile which must be followed by a hydraulic jump to enable flow to return to the normal depth. So it means that yes, hydraulic jump will form because it will pass through the critical depth. Clear? So it means that this Y2, which is the depth after the jump, can be taken as equal to Y0. It can be taken as equal to Y0 10.22 feet. So now this is the depth that we are assuming immediately after the jump. Clear? Y2, which is taken as equal to this is now what we are assuming, that this depth immediately after the jump, this is your Y2, which is same as Y0. Clear? So this we are assuming as Y2. Now immediately upstream of the jump, this is the depth. So this we need to calculate. Clear? This we need to calculate. Let's say this is Y1. So now this Y1 we can calculate because we already developed the relationship for a rectangular channel, how to calculate the depth before and after the jump. Clear? So what we can do is that now Y1, which is the depth immediately upstream of the jump, that will be equal to Y2 divided by 2 into -1 plus square root of 1 plus 8q square divided by g into y2, this is cube, and this is whole square root. Clear? So this whole is square root. Now you put the values. So when you put the values, we can easily now calculate y1. So this y1, this will be equal to 2.093. 2.093 feet. This is now the depth upstream of the jump. Clear? Now you can see here that at this point, just downstream of the gate produces the depth here. Let's say this is the section here. So at this point here, the depth is what? 1.6 feet. This is the depth here. Because we operate this gate 1.6. And now from 1.6, it will go to 2.093. Y1 is here at this point here. This is now the section here. Let's say this is section number 2. This is section number 2, and this is section number 1. So you can see here that the depth increases from 1.6 to 2.093, and then a hydraulic jump will form, and after the jump immediately the depth, that is 10.22 feet. So it means you see M3 profile, a rising profile. So the depth will increase 1.6 to this 2.093. Now hydraulic jump will form, and if so, find using one reach the distance from the gate to the jump. So now it means we have to calculate the distance from the gate, which produces this 1.6 feet, to Y1, because after Y1 we have this hydraulic jump. So it means that essentially we have to calculate this distance between section 1 and section 2. This distance actually we have to calculate. Location of the jump, delta x. So now in the previous lecture we studied that how we locate the hydraulic jump. We studied that we apply the combined principle of rapidly varied flow and gradually varied flow. Together we apply the principles. So you have rapidly varied flow. You can see here that by application of rapidly varied flow, we are able to determine the depth before the jump. And now we want to locate the jump, that for example, how much distance this jump is located from the gate. So you can see here from the gate to the jump, this is an M3 profile. So what we will do is that to calculate this delta x, we can apply the gradually varied flow theory. The principles of gradually varied flow we can apply, and we can calculate this delta x. So that's why, remember, it is written in your textbook also that combined principles are applied when we want to locate the hydraulic jump. Clear? So for that case, what we have to do is that in this case, one reach we have to use. So that's why we just take two sections. You can draw a table, as we have already studied that for this case we will draw a table. So you have to take section, because we have two sections. So we consider section 1 and also we consider section 2. Now after this section, we will calculate the hydraulic radius. So the hydraulic radius, the depth, that will be equal to the hydraulic radius. Clear? Because we have wide rectangular channel. So this is in feet. And then after this we will calculate the velocity. So the velocity will be equal to the discharge per unit width divided by the depth of flow. So this will be in foot per second, FPS. And after this we will calculate the velocity head, because we need to calculate the specific energy. So that's why you can calculate V square by 2G, because this is head. So that's why the units are feet for this problem. And after this we have to calculate the specific energy. So the specific energy, remember, that is equal to the depth of flow plus we have the velocity head, V square divided by 2G. So this is energy, that's why the unit will be feet. Now in this case, for section 1, we can calculate the values here. So the depth is 1.6. We start from 1.6, which is produced by the gate. Clear? This will also be equal to the hydraulic radius. So the depth is, this is Y. This depth is 1.6 at the first section. The velocity you can calculate discharge by the depth. So this is the depth, the discharge is given. So this will come out to be 40.625. Then you can calculate the velocity head, take care of the system of units. So this will be equal to 25.63, 25.63, and then we can calculate the specific energy, which will be just the velocity head plus we have this depth of flow. So in this case here, this specific energy will come out to be 27.23. So this will be equal to 27.23. Since it is asked to calculate in one reach, so that's why for the second section the depth will be y1, which we calculated 2.093. Then you can calculate the velocity, that will be equal to 31.05. Velocity head 14.97. As you can see, the depth increases, so the velocity decreases, so that the same discharge is maintained, because discharge is steady flow, 14.97. Then we calculate the specific energy. So this comes out to be 17.063. Now after this the table continues. Now what we have to do is that we have to calculate now the average hydraulic radius. So now the average hydraulic radius, this is RH, this will be bar, this will be in feet. So this will be the average of the two. This is the hydraulic radius now. 1.6 plus 2.093 divided by 2. So this is how we will calculate the average. Clear? So this will be equal to 1.846. 1.846 feet. Now after this we will calculate the average velocity. So V bar, and this will be in FPS, foot per second. Now this will be the average of these two velocities, 40.625 plus 31.05 divided by 2. So this will be equal to 35.84. 35.84. Now why we need to calculate these average? Because you already know that next we have to calculate the slope of the energy line. So the slope of the energy line, which is S, that is actually equal to N into V bar velocity, because we are averaging the condition 1.486. Take care of system of units, so 1.486 for BG units. And we have this RH bar, two by three, and this is whole square. So now from here we will calculate this S, slope of the energy line. So this will be equal to 0.1243. Now we have to calculate delta X, that is the distance between the two sections, delta X. So we already know that this is equal to E1 minus E2 the specific energies at the two section difference divided by S minus S naught. S minus S naught. So from here, when you put the values, so this will be equal to 82.06 feet. Now you will get a plus sign. So now this plus sign means that section 2, This plus sign means that section 2 is downstream of section 1. If we get negative answer, as we obtained in the previous problems also that we solved, if you get negative answer here, then it does not mean calculations are incorrect. It would simply mean that this section 1, it is this. If we get negative sign, then it means that section 2 is upstream of section 1. Clear? So this is how we apply the concepts of rapidly varied flow and gradually varied flow in order to solve the hydraulic jump problem, and also we are able to locate. Clear? At this much distance, the hydraulic jump will form downstream of the gate. Clear? Now at this we stop the open channel hydraulics. Remember, open channel hydraulics is a very vast area, and we can discuss many topics in open channel hydraulics, but this is what is given in your syllabus. So actually we stop it here. But this hydraulic jump, we can discuss many things in detail, many more topics. So the next topic that we are going to study is similitude and dimensional analysis. This is chapter 7 of the textbook. Now in this figure, before we see the learning objectives, so in this figure actually a model is shown, 1:46.6. This is a scale model. Clear? This is being tested in the 100-meter long towing tank. Now towing tank is actually a water tank where tests are conducted on models of ships, boats, yacht, under controlled flow conditions, or you can say under controlled environmental conditions. Now this model which is tested here, when we do the analysis, the Froude number is the most important non-dimensional parameter that we need to consider, because when the boat or ship or yacht, when they move, because they interact with the fluid, and as a result of gravity the waves are generated. Clear? And these waves, they offer also resistance in addition to the skin friction resistance to the motion of these vessels. Clear? So when we do the analysis, in that case, the Froude number that we have studied so far and applied in the problems, so that is actually the important number that we need to consider in the analysis. Later on in the topic, you will see that why we need to consider this Froude number. So the Froude number, we have to consider important parameter. Clear? When we conduct tests on this. So let us see a small video, then we will continue with this discussion. This is a towing tank. You can see here that the model of a small boat that is tested subject to different conditions. The idea here is to evaluate the design parameters, that if it is subjected to different flow conditions, what is the behavior. You can see here the whole setup. So this is a towing tank where we test the different models under controlled conditions. You can see here the waves are created in the towing tank, and then the model is moved. So you can see here we are able to conduct these tests to determine the behavior or evaluate the design parameters. So you see that models like this, they are tested in the lab, in the towing tank, which is written here, so as to determine the performance and evaluate the design parameters. And we try to predict the performance of the actual structure, the full size, full scale device, apparatus or structure, and this can help us to improve our design. Clear? Now example like this, that will be of interest to the students of naval architecture. In naval architecture, they study about the design of such vessels. Clear? So they would like to do the experiments on scaled models, and then they transfer the results to the full scale device, that we call it as prototype, that is known as prototype. So prototype, we have the full scale device, the actual structure, and we have the model. Now learning objectives for this chapter. After completing this chapter, you should be able to understand the concept of model study for the analysis of the flow phenomena that could not be solved by analytical or theoretical methods. Now we studied earlier, even in fluid mechanics too. So we studied that, for example, we applied mathematics to solve the fluid flow problems. Then in the hydrodynamics, this area which was called hydrodynamics, the fluid was treated as ideal. When you treat the fluid as ideal, so it means that it has no viscosity, and we want to calculate how resistance to the flow occurred. When a body is moved through the fluid, for example, train, car, aeroplane, they are moving through the air, or a submarine, for example, fish, it moves through the water, how resistance to the movement occurs. So only alone the theory cannot solve all the time all the problems. So that's why what we do is that we do experiments, and experimentally we studied the fluid phenomena in order to understand the concept and do the analysis. Clear? So in this chapter, actually you should be able to understand the concept of the model studies. Model studies are required. The reason is that only analytical or theoretical methods sometimes are not sufficient to explain fully any fluid phenomena. you should be able to understand the laws of similitude, which provide a basis for interpretation of model results. So it means that when we conduct a model study, how we interpret those results, just like you saw in the video for a small boat. So the tests were conducted. Now that you get the results, so how we interpret those results, what those results mean. And because we conducted the tests on models, for how we can transfer those results to the prototype, the actual structures. So for that we need some mechanism so that we can predict the performance of the actual structure by conducting tests on the models. So for that we have laws of similitude. Similitude is the theory and art of transferring the results of model to the prototype or vice versa. So you should be able to understand these laws of similitude. We will study in detail similitude, which provide the basis for interpretation of the model results. And we will study dimension analysis to derive equations expressing a physical relationship between the quantities. Now, this is actually second part of this chapter. So first we will study about the similitude, the model studies that we conduct, how we interpret the results. And then in the second part of the chapter, we will study about a dimension analysis. Actually, it's a mathematical technique where we deal with the dimensions of the different quantities, and it is used to derive equation expressing the functional relationship between the physical quantities. So this dimension analysis is a very powerful technique. It helps us to develop a functional relationship between the variables involved in any phenomena. And also this is used in the design of experiments, because you can see here we have model studies. So how many experiments you need to conduct. So this dimension analysis can also help in the design of experiments. So by the end of studying this chapter, you should be able to understand these basic concepts. Now let us start with similitude or similarity. So this is similarity between what? So similarity between the model and the prototype. Because we have to conduct experiments on models, and then we have to transfer those results to the actual structure that is called prototype, there must be similarity between the two. Clear? So this we are going to discuss in detail in the coming slides. Now, this similarity or similitude is the theory and art of predicting prototype performance from model observations. So what is similitude? We conduct test experiments on the models, and then we predict the performance of the prototype. The prototype is the full-scale device, apparatus, or you can say the actual structure. So this is known as similitude. Now this similitude means that we are predicting the performance of the prototype by conducting model studies. So there must be similarity between the two. This we are going to study in detail. Only then we can transfer the results. Clear? For example, you want to test the design parameters for an aeroplane. So you have to make a model similar to the aeroplane. it is not possible that we conduct tests on a car and transfer the results to the aeroplane. So that's why we see that similitude, similarity. There must be similarity between the model and the prototype. Then we can transfer the results between the two. Now, experiments are performed to obtain information that cannot be obtained by analytical means alone. So since only theory is not sufficient to explain the fluid phenomena, so that's why experiments are performed to obtain the information. Clear? And this similarity laws that we are going to study, which enable us to experiment with a convenient fluid such as water or air, for example, and then apply the results to a fluid that is less convenient to work with, for example, hydrogen, steam, or oil. Clear? So this is the advantage of this similitude or similarity. We can work with more convenient fluids, and then the laws of similarity laws, we can apply the results to fluids that are less convenient, for example, oil, steam, etc. Clear? So present engineering practice makes use of model tests more frequently. Now what we are observing is that not only civil engineering, but in other fields of engineering, for example, we have industrial engineering, mechanical engineering, aeronautical engineering. Clear? You saw the video of a small boat, naval architecture. So the present engineering practice is that we are frequently conducting tests on models, and then we evaluate the performance of the prototype, the actual structures, the full scale device. Clear? For example, why we do like this, that we conduct tests on the models. For example, you design the Turbela Dam. Now Turbela Dam is the largest earth and rock filled dam in the world, and it is very costly. So you want to test the design parameters. So is it possible that you can construct the Turbela Dam 10 times, 100 times full scale just to test the or evaluate the design parameters? It's very difficult, not possible, also very costly. So instead what we can do is that we can develop a scaled model of the Turbela Dam in the laboratory, and then we can test it subjected to different flow conditions, and we can evaluate the various parameters, and then from there we can predict the performance of the prototype, the actual structure. So this is more convenient and it is less expensive. So for example, whenever a new airplane is being designed, tests are made not only on the general scale model of the prototype airplane, but also on various components of the plane. Numerous tests are made on individual wing sections as well as on the engine pods and tail sections. So what we see here in this example is that whenever a new aeroplane is designed, so various components of the plane, they are evaluated, means the design parameters. So what they do is that numerous tests are made on individual wing sections, engine parts, tail sections, etc. So it is less expensive when we conduct the tests on the scale models, and also it will help improve the design parameters, because when we actually construct the full scale device, the prototype, so the design will improve. Clear? We can improve our design from these model tests. So this is just one example. I give you the example of the Tarbela Dam. So what we do is that we want to conduct tests on models and then transfer the results to the prototype. This way we can evaluate the design parameters and it can help to improve our designs. That's why this similitude, this is very important, that we need to understand and how to use it. It has wide applications. Clear? So similitude is what? It is just simply the theory and art of predicting prototype performance from model observations. Let us continue with this. The laws of similitude enable us to predict the performance of the prototype, which means the full size device, full scale device apparatus, or the actual structure. That is the prototype from tests made with the model. So the laws of similitude, we will study in detail what are the laws of similitude that enable us to predict the performance of the prototype from tests made with the model. Clear? A few examples where models have been used include ships in towing basins, which you saw the picture also, and I show you the video. Airplanes in wind tunnels, hydraulic turbines. We study about the hydraulic turbines in fluid mechanics 2 course. Centrifugal pumps, spillways of dams, river channels. Study of such phenomena such as the action of waves and tides on beaches, soil erosion, and the transport of sediments. So you can see here that these models, they have been used for many applications. Clear? That's why we need to study that what is similitude, and then how we use the laws of similitude that will help us to predict the performance of the prototypes. So you can see here that model studies, they are conducted in many areas of engineering. Civil and environmental engineering, models of hydraulic structures, river sections, estuaries. Estuary means that where the river joins the ocean or sea. We have the coastal bays and seas. So you can see here, these are some of the applications in civil and environmental engineering. Mechanical engineering, models of pumps and turbines, automobiles. Naval architect, they develop ship models. Aeronautical engineering, model test in wind tunnels. So you can see here that a model of a boat is tested. Then we interpret the results and we transfer the results to predict the performance of the prototype, the actual structure. In this, here you can see that the model of an aeroplane, it is tested in wind tunnels. Clear? And then we evaluate the different design parameters. We improve, it helps us to improve our designs. In here you can see here that we have a model of a car, and the streamlines are shown, and also already we studied about this in fluid mechanics 2 course, forces on immersed bodies. So we want to minimize the drag forces so that it can move faster and fuel efficient. We already studied about this. So you can see, and if you remember that the shape of this car over the years has been modified. The idea is that you can see here the streamlines as closely as possible that follow. Because if there is separation, then what will happen is that the drag forces that will increase, and when the drag forces increase in magnitude, then more resistance will be offered to the motion. So you can see here that these model tests can help us to improve our designs, and we can predict the performance of the prototypes.
सर ये हमारे
Now,
डिपार्टमेंट में जो
Gigi,
सर हमारे डिपार्टमेंट में जो स्ट्रक्चर्स बनते हैं सर आर्टिक सेंटर में शेकिंग टेबल टेस्ट के लिए उसको भी सिमिलिट्यूड कहते हैं सर.
so in that case, you see similitude is you conduct a test on a scale models. And then from the model, you predict the performance of the actual structure. This is similitude. Now in here, I give you the different examples that this similitude can be used in many areas of engineering. So now that if in earthquake engineering you construct a small model and you test, and then you predict the performance of the full scale structure, so that is also similitude. This is the main idea behind this. Now, because we study fluid mechanics, so that's why here most of the hydraulic structures, river section, estuaries, coastal bays, and these are written. Now, this is not that the discussion of similitude is limited to only these cases. In any area, you see this is naval architecture. Now, we do not study design of, aeroplanes, etc. This is aeronautical engineering. Now this is mechanical, essentially mechanical engineering area. So in any area of engineering where you conduct tests on models and then you predict the performance of the prototype. That's why we use the term prototype. Prototype means the full scale device, the full scale apparatus, the full scale structure. You predict the performance of that. So in that case, this is similitude. So this can be applied in any area of engineering. If you understand the basic concepts and the basic idea, it is not limited to just that we can only apply this in our hydraulics lab. Is your question clear now?
Yes sir, clear हो गया sir. Thank you sir.
Okay, to continue with this, now it's coming. So you will see that it's not only that we can have similitude in fluid mechanics. It has applications in many areas of engineering. So first we start that now we have to conduct a model study, and then we use the laws of similitude, similarity. Those laws we will study in detail, and how we transfer the results between the two. So first we learn what is a model. So a model is a representation of a physical system that may be used to predict the behavior of the system in some desired respect. Which design parameters you want to test. So what is a model? A model is simply representation of the physical system. Now that physical system can be a river, can be a dam, can be a structure of a building, can be a car, can be anything. So it is representation of that real world system, physical system, that may be used to predict the behavior of the system in some desired respect, what you want to check. So you can see here that this is the model of an aeroplane, this is the model of a dam, and now here comes, you ask a question, this is the model of a high-rise building, and it is subjected to the wind load. You can subject this to earthquake loading also if you are interested. So it is subjected to the wind load. This is a model, clear? And then we would like to see that how it behaves to the wind load. And then we can predict the performance of the prototype using similarity laws. Now, in these examples, you can see that the model that is small as compared to the prototype. So we have the model that we are discussing, and then we say that we have prototype. Prototype means the actual structure. Now, the model in our case, in our civil engineering, or you can say fluid mechanics or hydraulic engineering, in general, the models are smaller than the prototype. For example, model of a dam, so generally should be smaller. Similarly, you have the spillway or the river model, should be smaller. You can see here the building model shown should be a smaller. But this is not always the case, that the model will be smaller than the prototype. In some cases, it is also possible that the model can be larger than the prototype. For example, we might study the, let me take an example, we might study the flow in carburetor. You studied mechanical technology course, there you might have studied introduction about internal combustion engines. So there we use a carburetor. What is carburetor? If you remember, it mixes the air and the fuel in the required ratio for combustion. So that is small size, clear? So we might study the flow in a carburetor in a very large model. Maybe we would like to study that phenomena in a large model to better understand and then transfer the results. Similarly, we might investigate the flow of water at the entrance to the small centrifugal pump runner by studying the flow of air at the entrance to a large model of the runner. In that case also, it might be possible we have a large size model as compared to the prototype. So remember, the model commonly we observe here in application that it is okay small than the prototype, but it is possible that in some cases the model may be larger in size than the prototype. So this is not an issue. We will see how convenient it is to build a model smaller than the prototype or larger than the prototype. The idea is to better understand the phenomena, the physical system, and then we predict the performance of the prototype. Clear? For example, in this case, let me show you a small video here. So you can see here we have a small fly. Now you want to simulate its behavior, how it flies. So you can see here that the model that is developed to simulate, that is bigger in size than the prototype. You can see here it is bigger in size. So now that is flowing through the air. Here the medium may not be air, maybe we want to check it in a different fluid medium. It is still possible. We can interpret the results. This is what we learn in this similitude or similarity concept. Clear? As I earlier said, that these similarity laws, they enable us to experiment with convenient fluid, for example water or air, and then apply the results to fluid that is less convenient, for example hydrogen, steam, oil, etc. Clear? So now what is a model? It is a representation of the physical system that may be used to predict the behavior of the system in some desired respect, what you want to test. And it may be smaller or may be larger. Clear? So it's not that model means that it is always smaller than the prototype. In some cases, it can be larger than the prototype. Now, what is justification for the models? Economics. A model being small in our case, for example, now we study hydraulics. So in hydraulic, we study river or dams or spillway. So a model should be generally small. So a model being small compared to the prototype, so it costs little. So you want to make a model of a dam. Now you design a dam, you want to test it for different flow conditions. So if you produce a model and then subject it to the different flow condition in controlled environment in a laboratory, that will cost little, clear, compared to the prototype. So this is justification for the model studies. The second point is practicability. In a model, environmental and flow conditions can be rigorously controlled. So because we develop the model, as you saw in the towing tank for that model of a ship or boat, you have control over the conditions and you can change the conditions, and then you can test or evaluate the performance of the design parameters. So you can see here in the model, it is the practicability is more as compared to the prototype conditions. There, how you can have control over the flow conditions, very difficult. So that's why you see that in model you can subject it to a very vast variety of flow conditions and then evaluate the performance. So that's why now this area of model testing has become very important in different areas of engineering. Now, conditions which must be satisfied for similitude between model and prototype. Now, so far we understand what is a model, what is a prototype, and the importance of the model study that and this is increasingly over the years, these model studies extensively are conducted in different areas of engineering in general to improve the design, to evaluate the performance of the prototype. We predict from the model results. So how we do this now? Now that we want to develop a models that can help us to predict the performance of the prototype. So how we do it? There must be some criteria which will help us to predict the performance of the prototype from model and vice versa. So conditions which must be satisfied for similitude. Similitude means similarity. There must be similarity between the model and the prototype. Only then we can predict the performance. As I said before, you cannot conduct test on a car and then predict the performance of an aeroplane. So that's why we must have similitude between the model and the prototype. Only then it will be possible to transfer the results. So what are those conditions now? So the first thing is geometric similarity. There must be geometric similarity between the model and the prototype. We will study this in detail. There must be kinematic similarity, and there must be dynamic similarity between the two, model and prototype. If these conditions are satisfied, then we will be able to predict the performance of prototype from the model results. So what we mean by this, the geometric similarity, it means that the model must be of the same shape as the prototype, but may be scaled by some constant scale factor. So it means that the model and the prototype shapes must be the same. Clear? This we have to ensure. Just like I said, you cannot say that, okay, let me conduct tests on a car and then I will predict the performance of an aeroplane. So that's why we have to ensure this. The second thing is kinematic similarity, means that the velocity at any point in the model flow must be proportional by a constant scale factor. I will explain what we mean by this scale factor, to the velocity at the corresponding point in the prototype. So it means that the velocity vectors which will be acting, because the model and the prototype, they are subjected to the flow condition. Now we are discussing this specifically from hydraulics point of view. So the model and the prototype, they will be subjected to the flow conditions. So there will be velocity vectors. They should be the same in the model and prototype at the corresponding points. The same, I don't mean that the same value, but the velocity vectors should be at the same points in the flow in the both the model and the prototype. They can only differ by a scale. Just like the shape must be the same, but only differ by a scale, big or small. So similarly here it says the velocity at any point in the model flow must be proportional to the velocity at the corresponding point in the prototype. And the third one is dynamic similarity, means that when all the forces in the model flow scale by a constant factor to corresponding forces in the prototype flow. So it means that the forces which are acting in the model, the same forces should be acting essentially in both, in the model and in the prototype. Only they can differ by the scale. For example, if a force of 10 Newton is acting in the model, so maybe a force of 100 Newton acting in the prototype, but the same forces should be involved. By the same forces, I mean that if, for example, we have, let's say, we have, for example, let's say viscous forces. So viscous forces, when they are dominating, we already know that the Reynolds number, it is less. And we have essentially the conditions of laminar flow. So it means that when we have laminar flow in the prototype, in the model, we should also have laminar flow. Because let's say in the model, if we have laminar flow, and in the prototype we have turbulent flow conditions, so in that case, then your results will not be accurate if you transfer the results from the model to the prototype. So it means that when we consider the forces, the different forces we will study in detail, that can be the pressure force, the elastic force, can be the viscous force. So if these are significant in the model, should also be significant in the prototype. Means that there should be similarity when we consider the shape, when we consider the velocity, kinematic conditions, or dynamic when forces are involved. So there must be similarity between the two. They can differ in scale, small or big. So if we ensure these similarity conditions, then we can accurately transfer the results from the model to the prototype and vice versa. Only then this concept will work. So this we are going to study in detail how we ensure this geometric similarity, kinematic similarity, dynamic similarity. From here onward, we will develop the laws, and then using those laws, we will be able to predict the performance of the prototype from the model tests. So let us take a break, then we will continue after the break.